Hi, welcome to my channel. In this lesson, I'm going to discuss some few questions in capacitors. Okay, the first question about charging a capacitor. A capacitor of capacitance 1000 microfarad is charged through a total resistance of 20 kilo ohms by using a DC power supply of EMF 16 volt. So the power supply might have internal resistance, but that resistance also included as the total resistance because all are in series connection among them. So the resistance of the wires, resistance of the capacitors, internal resistance of the cell, everything is totally included as total resistance 20 kilo ohms. Okay, so the first question, find the initial current. Okay, we know that initial current, so initially there is no voltage across the capacitor because capacitor has no charge. So voltage across the capacitor initially will be equal to 0. So the initial current is only due to the total resistance of the circuit. So initial current is given by I naught equal V naught, that is 16 over 20,000. So you'll get it in amperes. So that will be 800. If I give it in 800 milliamperes, 10 to the power 6 microampere. So it's going to be 800 microampere. Okay, I can give it in ampere, but I just put it in microampere. Otherwise, there will be a lot of decimal points. Okay, second part, find the time constant. We know that time constant is given by RC. So time constant is equal to RC. So R is 20,000, 20 into 10 to the power 3 times capacitance, 1000 microfarad, 1000 times 10 to the power minus 6. That will be 20 seconds. We know the time constant unit is seconds. So this will be 10 to the power minus 6, here 20 seconds. Right, that's right. Third part, find the voltage across the capacitor at 30 seconds. That's the third part. Find the voltage across the capacitor at 30 seconds. Okay. So when the voltage across the capacitor 30 seconds, if they ask, we should find the current at 30 seconds. Yeah. If I find the current at 30 seconds, that will be by using that current, I can find the voltage across the resistor. Then the voltage across the capacitor, I can call this as, I can name it VR. This is VC. At any instance, VR plus VC is equal to 16. So I'll find the current at 30 seconds. So I can simply find, I know the initial voltage of the resistor is 16. So the voltage across the resistor will decrease exponentially because current decreases exponentially. Okay, so I'll find the voltage across the resistor at 30 seconds. Then that voltage should be subtracted from 16. Then I'll get the voltage across the capacitor. I can find the current at 30 seconds, or directly I can find even the voltage across the resistor at 30 seconds. So I can say for the resistor, I can use V equal V naught e to the power minus T over C. So V naught, that is the initial voltage of the resistor at the charging process started, that will be 16 times e to the power minus 30 over RC is 20. So find the V, the voltage across the resistor, find it. So if you find the voltage across the resistor, that will be 3.57 volt. So voltage across the capacitor at 30 seconds, that will be 16 minus, total voltage is 16. So 16 minus VR, voltage across the resistor. I can say VR, voltage across the resistor. So 16 minus 3.57, that will be 12.43 volt. Okay, next part, find the charge of the capacitor at 30 seconds. So I found the voltage of the capacitor at 30 seconds. So I can use Q equals CV, fourth part. So I can use Q equal CV for the capacitor. I know the capacitance 1000 microfarad, 1000 into 10 to the power minus 6 into the voltage. I found it in the previous part, 12.43. So if we solve, we will get the charge that will be 0.120124 coulomb. I can give it in millicoulomb. That's going to be 12.4 millicoulomb. Okay, the fifth part, find the time taken to store a charge of 10 millicoulomb in the capacitor. Okay, so for that, I can find like this. When the charge is 10 millicoulomb and the charge stored in the capacitor is 10 millicoulomb, I'll find the voltage across the capacitor, right? Then I can find the voltage across the resistor when the charge of the capacitor is 10 millicoulomb. So fifth part, I can say Q equal CV for the capacitor I'm using. Q should be 10 millicoulombs, so 10 into 10 to the power minus 3 equal capacitance 1000 into 10 to the power minus 6 times V. So the voltage across the capacitor, VC I can say, the voltage across the capacitor, VC will be 10 volt. So voltage of the resistor will be 6 volt because 60 minus 10 is the voltage across the resistor. So voltage across the resistor at that instant will be 16 minus 10. That's going to be 6 volt. So the question is, they asked to find the time taken to store 10 millicoulomb charge. Means I should find the time taken for the voltage across the resistor to drop to 6 voltage from 16 voltage. Initial voltage across the resistor is 16. So how long will it take the voltage across the resistor to drop to 6 from 16? So I'll use the equation V equal V naught e to the power minus T over RC. I can use VR for the resistor I'm using. For the resistor or total resistance. So VR should be 6. V naught was 16 initially. E to the power minus T over RC we found in the previous part, time constant, we found it as 20 seconds. Okay, we need to solve it. I can write this 1 over e to the power T over RC and I can cross multiply and bring it down. So this will become e to the power T over 20 equal 16 over 6. Take both side ln. So when we take both side ln, operate by ln both side. So this will become T over 20 will become ln 16 over 6. Solve it and find the time. That's the time taken to store 10 millicoulomb charge in the capacitor. So if you solve it, the required time will be 53.3 seconds. That's the answer for that. Sorry, it's 19.6 seconds. ln 16 over 6 into 20. Yeah, that will be 19.6 seconds. That's the time taken to store a charge of 10 millicoulomb in the capacitor. 19.6 seconds. Okay, so next part, find the time taken to store 50%, that is half, is it? 50% of the energy that could be stored at the end of the charging process. Okay, so at the end of the charging process, the voltage across the capacitor will be almost equal to 16 volt. So that time it stores certain amount of energy, that is the next part, but the time taken to store 50% of that possible maximum energy. Possible maximum energy is the energy that could be stored at the end of the charging process. So I can say like this, the sixth part I can say at the end of the charging process, the voltage across it going to be V naught. So I can say the final energy of the capacitor is equal to half QV, I can say half CV square, anything I can use, but I would like to keep one constant, that is capacitance. So half C V naught squared, where I know that V naught, the final voltage across the capacitor will be 16 volt. So now the question is, how long will it take to store half of this energy? So that means I can say that half of this energy E is equal to half EF, right? So that is going to be half. So EF I can say half C V naught squared. Okay, so when it stores this half of the final energy, there will be voltage across it. Let it be Vc. So that I can say that again half C Vc squared. Okay, so when this amount of charge is stored in the capacitor, at that time, the voltage of the capacitor is going to be Vc. So that half Vc squared is equal to this much. So half C get cancelled. So Vc squared is going to be half V naught squared. So Vc is going to be 1 over square root of 2 times V naught squared. Square root is V naught, that will be 16. So 16 over square root of 2, that will be the voltage across the capacitor that time. And that will be 11.3 volt. So voltage across the capacitor will become 11.3 when the energy stored in it becomes half of the final energy. So when the voltage across the capacitor is 11.3, then the voltage across the resistor will be equal to 16 minus 11.3, that will be equal to 4.7 volt. So I need to find the time taken for the voltage across the resistor to drop to 4.7 from 16. And we know that the voltage across the resistor decay or decreases exponentially. So I can use V equal V naught e to the power minus TORC for the resistor. V equal V naught e to the power minus TORC. I can use it for the resistor. So V is going to be 4.7. That's the voltage across the resistor, 4.7. Initially, it had voltage across it 16 e to the power minus T over RC. We found in previous part, that is 22nd. Okay, so that's going to be e to the power T over 20 is going to be 16 over 4.7. Take both sides ln, so it will be T over 20 will be equal to ln 16 over 4.7. So if you solve this, you will get the answer for the time taken to store half of the or 50% of the final energy. So the final answer will be 24.5 seconds. So that's the time taken to store 50% of the final amount of energy that could be stored in the capacitor is 24.5 seconds. Okay, so next part, find the energy stored at the end of the charging process in the capacitor, that is. So that is nothing. I can say the final energy, that will be half CV squared, half the capacitance is 1000 microfarad, 1000 into 10 to the power minus 6 into 16 squared. So that will be 0.128 joules. Okay, the last part, the eighth part of it, that is find the total work done by the DC power supply. So W equal QV, that's the work done by the DC power supply. The total charge flown, we know that already we found, we can find that the total charge flown in the capacitor, that is 0.16 coulomb. Or we can find that finally Q equals CV. So C is 1000 microfarad, V is 16. So if you want, I can find that Q equals CV. C is 1000 microfarad, 10 to the power minus 6 into the voltage is 16. So that's the total charge flowed in the circuit during the charging process into the voltage across the capacitor, that is 16. So that will be equal to 0.256 joules. You can see that this is 50% of this one. So what happened to the other 50%? No other explanation. We can say the energy is converted to heat due to resistive part of the circuit. Okay, so this is the second question in which it says a capacitor of capacitance 2200 microfarad is charged up to 12 volt and then it is discharged through a total resistance of 30 kilo ohms. First part, find the initial current when discharging the capacitor. So initial current will be at the moment its switch is closed. So when it is discharging, the switch should be closed. When the switch is closed, the initial current will be I naught will be the voltage across the initial voltage across the capacitor 12 divided by the resistance 30,000. So the initial current will be 400. That will be 400 microampere. You'll get it in amperes, convert to microampere. So 10 to the power 6 microampere. That will be 400 microampere. Second part, find the time constant. So the time constant, we know that time constant is given by RC. So time constant equal to RC, that is the resistance is 30,000 into capacitance 2200 10 to the power minus 6. So that will be 66 seconds. That's the time constant. Okay, so third part, find the charge of the capacitor at 4 seconds. And we know that during the discharging process, the charge of the capacitor also will decrease exponentially. So we'll find the initial charge of the capacitor. So that is Q naught is equal to CV. We know the capacitance 2200 10 to the power minus 6 into initial voltage was 12. So the initial charge of the capacitor will be 0.0264 coulomb. I can give it in millicoulomb. It will be 26.4 millicoulomb. So the charge of the capacitor at 4 seconds, during the discharging process, all three factors, voltage across the capacitor, discharging current flow, and the charge of the capacitor, all three will decrease exponentially. So for the capacitor, I can use Q equal Q naught e to the power minus T over RC. So Q naught is 26.4 millicoulomb times e to the power 40 over RC. So RC I already found it 66. So solve it, you will get the answer for the charge at 40 seconds. The answer will be 14.4 millicoulomb. Okay, the next part, find the time taken to lose 50% of the initial energy stored in the capacitor. So I can say the initial energy stored in the capacitor is given by I can say EI, initial energy, that is given by half C V naught squared. So V naught is 12 volt. It was initially 12 volt. So now I should find the time taken to hold or time taken to lose 50% of this energy. So when it loses 50% of that energy, the energy remaining in the capacitor will be 50%. So I'm using this energy stored in the capacitor is 50% because 50% is lost. Say in case if they ask find the time taken to lose 60% of the energy, means the energy remaining will be 40% of the initial energy. Okay, if they say the time taken to lose 70%, means if it loses 70%, then the energy remaining will be 30%. That is, I should find 30% of this one will remain there. But here it's simple, they ask to find the 50% of the energy. So if it is 50% of the energy is lost, means 50% will remain there. So the energy remaining in the capacitor will be 50% of this. So that is 0.5 into half of CV0 squared. But at that time, when it holds 50% of the energy, there will be voltage across it. So that I can say half C VC squared. That VC is the voltage remaining in the capacitor when it holds 50% of the initial energy. So half C and half C will get cancelled. So VC squared is going to be 0.5, or that is half V0 squared. So VC is going to be 1 over square root 2 of V0. But V0 we know 12. So that is going to be 1 over square root of 2 into 12. So that VC will be equal to, it has a value that VC will be equal to we'll find that value VC. Okay, we'll find that value without substituting the V0, and I can give you a conclusion at the end. So VC should become 1 over square root of V0. So I can say the voltage because the capacitor is decreasing. So VC is equal to V0 e to the power minus T over RC. That's the way the voltage because the capacitor is decreasing. Now the VC has become 1 over square root of 2 V0 equal V0 e to the power minus T over RC. So actually in this question, this part, when it is storing 50% of the energy, it does not depend on the initial voltage because V0 is going to get cancelled. So both sides V0 will get cancelled. So 1 over square root of 2 is equal to e to the power minus T over RC is 66. So remember that whatever the initial voltage, to lose 50% of it, it does not depend on the initial voltage. So we not get cancelled. I can find the time, take both sides ln. You know how to solve it like previous question. So if I take ln on both sides, it will become, I can write it's 1 over, so e to the power t over 66 equal ln square root of 2. Find the t. If you take ln both sides, it will become t over 66. T over 66 is equal to ln square root of 2. Find the t. That will be 22.9 seconds. Okay, the last part of this question is estimate the minimum time required to completely discharge the capacitor and justify your answer. But you know that theoretically the time taken to completely discharge the capacitor is infinite time. You know the graph never touches the x-axis. If I plot a graph of charge of the capacitor against time, so the capacitor, the charge of the capacitor decreases exponentially, and we know this time axis is an asymptote. It never touches the time axis. That means the charge stored in the capacitor never becomes zero theoretically. But we can estimate the minimum time, how long it will take practically. I can say practically the capacitor is almost discharged. If I want to say, sometimes in the past paper questions, Edexcel, they used this idea. So if I want to say the time to almost completely discharge, the minimum time, I can say 5 times of the RC. Okay, so if I say the time required to completely discharge the capacitor, that is equal to 5 RC, any value I can say more than 5 RC, 6 RC, 7 RC, 1000 RC, 5000 RC. But those are overestimated times. The question is minimum time. So minimum time is 5 RC is enough. 4 RC is not enough. 5 RC is enough. So they ask you to justify your answer. Okay, now I can check how much of charge will remain in the capacitor at the end of 5 RC. We'll see that Q equal Q naught e to the power minus T over RC. So when 5 times of the RC elapsed, 5 times of the RC is that's the time duration of discharge, means the charge remaining will be Q naught into e to the power minus 5 RC over RC. RC will get cancelled. It's going to be Q naught e to the power minus 5. That is Q over Q naught, the fraction of charge remaining in the capacitor. This is the initial charge of the capacitor. This is the charge remaining in the capacitor when the time becomes 5 times of the RC. That will be e to the power minus 5. If you find it, that will be 0.007. 0.007, or I can say in percentage it's going to be 0.7 percentage. I can say 0.7 percentage of the initial charge will remain there. 0.7 percentage of Q naught will remain, means how much it discharged. 99.3% of the initial charge is discharged. So practically we can say the capacitor is almost discharged. So I can take the minimum time to completely discharge. Theoretically, it never comes to completely discharge that situation, but I can say practically the time required to completely discharge will be almost 5 hours. That's the minimum time. Okay, so third question, that is very simple. A capacitor of capacitance 2200 microfarad is charged to 16 volt. Find the charge of the capacitor. Second part, find the energy stored in it. So those are very simple questions. So first part, I can say Q naught, that's the initial charge. Q naught equals C V naught. So the capacitance is 2200. 10 to the power minus 6 into the voltage 16. So you will get answer that is 0.0352 coulomb. Normally I give it in millicoulomb to avoid unwanted too much of decimals. So that will be 35.2 millicoulomb. Second part, they asked to find the energy stored in the capacitor. So the energy stored in the capacitor, I can say the initial energy half QV I can use, or CV square half QV. So half the charge of the capacitor is 0.0352 into the voltage is 16. So you will get answer that will be 0.282 joules. Okay, the third part of this question says that the capacitor 2200 microfarad capacitor is removed from the power supply, that was 16 volt power supply, and now this capacitor is connected across an uncharged 1000 microfarad capacitor. So what will happen, this charged 2200 microfarad capacitor will function like a DC power supply, and it will charge this uncharged 1000 microfarad capacitor. So the charges will be transferred, a certain amount of charges will be transferred from this capacitor to this one. Up to when will it happen? This will happen until the voltage across the both capacitors become the same. Initially, this has no voltage across it because it was uncharged capacitor. This has 16 volt. So charges will flow from this capacitor 2200 microfarad to 1000 microfarad until the voltage across both capacitors become the same. We need to find the new voltage at steady state. Steady state means when the charging process comes to end. Okay, so I can find like this. When the charges flow from one capacitor to the other one, the total charge will remain unchanged. The total charge will not change. You can't create or destroy charge. Only the charges can be transferred from one capacitor to the other one. So I can say at the steady state, the charge of this capacitor is Q1 and the charge of this capacitor is Q2. If I take like this, Q1 plus Q2 will be equal to the initial charge of the 2200 microfarad capacitor, that was, we found it 0.0352 coulomb. Okay, so I can say at steady state, that is third part, eighth part, I can say at steady state, Q1 plus Q2 will be equal to the initial charge of the 2205 microfarad capacitor, that is 0.03. I can put it in 0.0352 coulomb. But Q1 is equal to C1V. I can call this capacitance C1, this as C2, and I will substitute the values later. So C1V, both are going to have the final same voltage, plus C2V is equal to 0.0352. So I can take the V common, that is, if I take the V common out, so it will become V into C1 plus C2 is equal to 0.0352. Substitute C1 plus C2, 2200 plus 1000, that is 3200. So V times 3200 microfarad, so 10 to the power minus 6 is equal to 0.0352. This will be the final steady voltage. Solve it, you will get the answer. So that will be equal to 11 volt. So 11 volt is the final steady voltage, right? Next part, find the charge on each capacitor. So that's simple. I can say Q1 is equal to C1V. Q1 is equal to C1V. So C1, I know that 2200, 10 to the power minus 6 into 11. Solve it. You will get the charge of Q1, that is 0.0242 coulomb. Same way, Q2 is equal to C2V, C2, that is 1000 microfarad, 10 to the power minus 6 into V is 11. So that's going to be 0.011 coulomb. Or you can subtract this charge from the total charge, you will get this one. Okay, C part, find the total energy of the capacitors and compare it with the value calculated in part 2. Okay, so we found the charge of the capacitors at steady state. We know the voltage. So I can find the total energy at the end of the charging process, or at the steady state. Half C1 V square plus half C2 V square. So that's going to half C1 plus C2, that is C1 plus C2 is equal to 3200 micro 10 to the power minus 6. I took the V common, so that's going to be, the V is the final steady voltage, that will be 11 squared. Okay, so this I can write half C1 plus C2 into V square. V is the 11 squared. Okay, if you solve it, you will get the final total energy of the capacitors. Okay, so that will be 0.194 joules. But we found in the second part, we found the total energy stored in 2200 microfarad when it was charged. It was 0.282 joules. Yeah, now the energy is less. So what's the reason? Now the total energy dropped. What's the reason the total energy dropped? The reason, when the capacitors are connected in parallel, there will be charge flow, there will be current flow. So due to the current flow, a certain amount of the initial energy stored in the 2200 microwatt capacitor is converted and dissipated in the form of heat. So that's the reason the final total energy is less than the initial energy stored in 2200 microfarad capacitor, because during the charging process of 1000 microfarad from 2200 microfarad, certain amount of electrical energy is converted to heat due to the resistive part of the circuit, and it lost to surrounding. Okay, so the first part can be done like this also. Edexcel students, they don't have series connection and parallel connection. So that's the reason I did not use the equations for series connection of capacitors, equivalent capacitance. I didn't use that concept. But Cambridge students, other exam boards, AQA or even International Baccalaureate, they can use that. So if I use that way, the first part, so these capacitors, when the 1000 microfarad capacitor is connected across uh, the 2200 microfarad capacitor, we can imagine they are connected in parallel. They are connected in parallel, yeah. But we don't know the charge, so I can say the charge of it is Q1, charge of this is Q2. The equivalent capacitance of parallel connection is equal C1 plus C2. That is going to be 1000 microfarad plus 2200. That will be 3200 microfarad is the equivalent capacitance of the parallel connection. And we know that when capacitors are connected in parallel, the charge stored in the parallel capacitor, the equivalent capacitor, charge stored in the equivalent capacitor will be equal to sum of the charges stored in the parallel connection. So if I say the parallel equivalent capacitance is 3200 microfarad, the charge it consists of is Q1 plus Q2, and we know that Q1 plus Q2 is equal to Q. Charge cannot be created or destroyed. So that initial charge of this one, the first part what we found, 0.0352 coulomb, will be the charge stored in the equivalent capacitor, because Q1 plus Q2, the charges will be shared among them. Charges can be created or destroyed. So if I say at steady state, the charges are Q1 and Q2. Q1 plus Q2 is the charge of the equivalent capacitor. So I can use Q equals CV for the equivalent capacitance. If I use it, Q I know that is the initial charge stored in 2200 microfarad. That will be 0.0352. The capacitance is 3200 microfarad, 10 to the power minus 6 into V. Find the V, that will be 11 volt. So 11 volt is the voltage across the equivalent capacitor. Careful, that's the voltage across the equivalent capacitor. I'm using this for the equivalent capacitor. So I found the voltage across the equivalent capacitor, but I thought that in my previous video, I told that when capacitors are connected in parallel, the voltage across the equivalent capacitor will be same as voltage across each and every capacitors. Those are connected in parallel. So I found the voltage across the equivalent capacitor. That will be the voltage across these two capacitors when they are connected like this. So that way also I can find the equivalent, I can find the final voltage, but this answer won't be given in the mark scheme Edexcel, because Edexcel you don't have equivalent capacitance, but other exam boards will follow this method.